Hi there, welcome back. So let's work in tutorial 7. So if you download the cases, you should have these folders. So let's go in Fluent case and I will open the base case. Okay, we're working in this one, but remember that you have geometries, everything, different meshes, so you can use different cases. So I already launched Fluent and I will go case base. Okay, I have it here and Fluent case base. So this is the main case that we're going to use. I want to point out here that you will find these files. So here you have the experimental data. So we know how to open. In any case, we're going to do it again. So this is the Fluent format. And then we have these two files here. These are profiles, velocity and kinetic energy, dissipation, and omega fields to use it as in the condition. We're going to see how to open that. Okay. So here we have the case. And as you go here, mesh, this is our mesh. So as you see, this is a nice mesh, fine mesh. So it's a wall resolving, or let's run. So let's see what y plus value we have. But also see that in this line here that we already saw that we're going to do the sampling already. Everything is pretty fine for you already. So remember that we have the vertical approach, so I'm just going to browse fast here because we know what is going on here. So general, steady case. Then in models, for the moment, we just need to enable viscous models, the one that we're interested in, the turbulence. And the base case, we're running K-epsilon, realizable, enhanced wall treatment. So just let me say something about here. So you have the K-epsilon and you have the three formulations here: standard, RNG, realizable. All of these are, let's say, different formulations or variants of the standard, RNG and realizable, that they have some improvement. So let's say that the realizable probably will be, of all this evolution, will be the best one, but all of them use wall functions. But remember that software developers, or they can add new enhancements. So see that here you have the option for near wall treatment. Okay, so if you put it like this, it will be pure wall functions. So you have to be careful. Remember that if you use wall functions in a wall resolving mesh, you are going to deteriorate the results. Okay, so this is contrary now to the notion that we have you make the mesh finer, you get better results. No, in this case you're going to get worse results. So we're going to run the first enhanced wall treatment just to see the results, and then we're going to run like this just to show you that we have worse results. And then these are corrections that later in further tutorials, okay, different geometries, we're going to see what they're doing. But for the moment, they focus in this one. So nothing to do here. Material, you select your materials. Nothing to do here. The full options are okay. So here you set your boundary conditions. Okay, so standard boundary conditions. But I want to point out that in this case already everything has been set up for you, that we have the velocity profile here. So as you enter into inlet, see that here we're reading this one. So by default, probably you have constant. We have done it using the constant. So if you use constant value, there will be a large difference. So we have these profiles. So you access here. So we have the X velocity profile. So the thing is that, let me show you how to plot this profile. So as you go here in the bottom, after you read those profiles, here you have the profile data. Okay. So to read those profiles, you go into File, Read Profile, and just locate the profile. So for instance, we're running K-epsilon, so the file RKE is the one that we need to read. If you are using the K-omega, you read this one. So if you select this one, okay, you read the file, already you have it in memory. So as you open this file, the text file also is a Fluent format, so you can go into the documentation to see how to set up, but basically see that you give a header and then coordinates. Okay, so you can take experimental data, DNS data, and other data that you put there. So after you read that profile, you go here, profile data, and you can plot it. Okay, so see that you access the variables. So I want to plot vertical. You go here, and this is your velocity profile, and then turbulent kinetic energy profiles and dissipation profiles. Okay, so this is much better than having a uniform profile. We're going to see that. So you read it, and then you will access those profiles here. Okay, so most of the time you may have some experimental data and inlet. So this is the way how you put it. Okay, so you have it there. Then you have the other external, the standard boundary conditions. So outlet, we're not setting anything. It's a pressure outlet, walls, everything is standard. Here we keep reading. Okay, so see mesh interface, nothing to do. These are advanced options here. Reference values just to normalize. So I put this one. This is to normalize coefficients and turbulence intensity and so on. And then methods. Okay, so far we have mentioned that the default method proposed by Fluent is okay, but if you want, you can use different options. You can do your own benchmarking. You will see that some will be faster, some will be slower. Okay, so it's up to you, but let's use the default option. So as you click here, default, this is what is Fluent proposing. So remember that momentum, second order of win, at least you need to have for final solution production runs, at least second order accuracy. This is what we want. When it comes to turbulence, first order it is acceptable, but it might be better to get second order or higher order. Okay, but for the moment, let's use first order. So controls, default values are okay, and if you're having problems with the convergence, recommend just to reduce these values, and usually will be the under relaxation related to the turbulent variables. Reports definition, remember to set up all your monitors. So see here that I'm setting many monitors. Okay, so it's up to you. Then you can review these monitors, but it's always set monitors. Okay, here your residuals, so you set up your residuals. See that it changed this one to let it run for a longer time, okay, because this one would reach convergence fast. Okay, so or you can disable that. Some plops, and that's all. Now let's go here, let's initialize. So I want to initialize with the values from the inlet, initialize, and we should be ready to go. So now you are here. Leave default values here. Let's run, put here a value. Okay, so if you reach convergence, it will stop, or will stop when you reach the maximum number of iterations. See also that mention that even if this case is steady, you can compute statistics. So if you are interested in getting a statistic, and usually this is helpful when you have some unsteadiness, not some shedding in your steady solution. So it's a good idea to do it. But in this case, I know that I don't have that, but you can enable, okay? There is not a problem, so you can put it there. So I will leave it on. And now I press calculate and see that all your monitors, everything. Okay, you have it here, the viscosity ratio at the outlet, then the wall shear stress. Okay, so this should be the average value either weighted in the wall, I think, in the bottom wall, and your Y plus. So see that we reach rather very fast convergence, 97 iterations. And see here you have your residuals. This is a smooth solution, good indication that we have converged. Y plus, see that it's not oscillating anymore, so good indication. Wall shear stress also not oscillating, so remember that this one will be related to this, or this to this. And at the outlet we have this output, okay, the area weighted average of viscosity ratio, that since that maybe it's still oscillating, but it's not that much oscillation, so probably you can measure that oscillation will be the RMS, or you can compute standard deviation. It's up to you. But here see that it's very smooth, so we can take this for granted. And now we go and see colors. So as you go here, see that this is velocity. You have access here to all the variables. Okay, so depending what you want to see. But I want to point out that see that we enable the statistics. So you go here, steady statistic, and see that now you can access here mean velocity value. So this is the iterative. So I see that there is a difference with the instantaneous and this one. See that we have a long initial transient, so we have some noise. So this is why it's not recommended to compute a statistic starting from the initial iterations. You need to discard this initial transit. So it might be better to start to compute that starting for 50. Okay, the same applies with on steady solutions. Okay, but in any case, you have access to that one. So you have here the root mean square of these variables. This you can see as the fluctuation, where you have largest fluctuation. As we expect, we have it here. Okay, where you have the recirculation, but also where you have the shear layer. Remember that here you have the flow coming at shear layer and boundary layers. So you have access to all that information, and then we can look at the field. So see that here's where your turbulent kinetic energy is kicking, where you have all your fluctuations, you can access dissipation, okay, so it should be at the wall where you are dissipating, okay, and so on. You have all fields. So let me put here velocity. Okay, so see that we have this, and now we can do more post-processing. So it's here in XY, you can access in walls. You can do plots in walls or surface, boundary surfaces. So here I already have a few predefined for you. So in the bottom wall, we can plot wall shear stress and precisely the X component. Okay, so see that the X component can take negative sign. It's not the magnitude that is always positive. So see that here when you see negative means that you have separation and reattachment. Okay, so you have access to all the components there. Then we have bottom wall. Okay, well, pretty much I think, yeah, that one's the same. Plot 3, let's see what we have here. So this is the distance normal to the wall. Okay, in the line we see here that we're sampling line 9, the line that we created. So you have here, you should have a surface, that line, and I put precisely that line in these coordinates. And here we have y, the distance normal to the wall, and here the velocity. Okay, so normal to the wall, this is your velocity profile in that line. Okay, and this one again, line 9, and here we're plotting u plus, again y plus. Okay, so remember that these are custom fields. They are not computed by default in Fluent, so you need to create it. So we're going to review how to create those. So see that we have our classical profile here. Okay, and see that we have it there, and let's change the scales probably. Okay, or better, let me load the solution data. Okay, we have case modes. Okay, we should have validation data. Okay, support files. So see that in support files you have validation data, and here you have loads the wall. And let me load here, for instance, a Spalding solution. And see that you put it there, and you have a nice agreement. Okay, so see that here our y plus, okay, which we haven't seen. Let me plot it here. So instead of plotting that one, let me plot here y plus, or y star should be similar. So these are your values that you have. So we have a y star, something about 8, or y plus. Okay, so you have your values there. So this is when we plot here. See that the first cell center in the line where we're doing the plotting, we have it here. Okay, something about 10. Okay, let's put again the solution so we can put the lows better. So see here that you have, and see that we have a relative good agreement here. We have a rather narrow overlap region, and then we have the defect region now that we separate. Okay, so in this case, for instance, you want to resolve the viscous layer. This is just telling you that you need to have a finer mesh. Okay, so it's up to you that you can redo this solution. But what is interesting that we have this one. Okay, we see that we have something similar to what the theory says. So we go here, we have the wall shear stresses, but we also have some experimental results. Okay, so you go here, okay, you have the CF data, and see that we compare, and we have a very good agreement. Okay, so the dots, the red dots that you see here, corresponds to an experimental results. Okay, so you have the links there, the references, and see there is a rather good agreement. Okay, there are some differences. Okay, there might be improved using finer meshes. It's up to you, but this is a very good, a very acceptable solution. Okay, so just to remind you again, let me replot the mesh. Okay, here, see that the velocity profile, we were plotting that here. Okay, you see this white line there is where we were plotting. Okay, so this is what you do. Okay, so remember, to do those plots, you need to compute wall shear stress. Then you sample in this line needs to be normal to the wall. In this case, a straight wall. There is no problem, but if you have curvature, you have the geometry, so you know how to generate this line. And then you sample in this line the velocity. Okay, velocity, and compute y plus in this line. So just to review how to compute those quantities, the y plus and the y plus normal and u plus. Remember that those quantities, they are not computed by default by the solver. So those are derived quantities. So as you go here, parameters and customization, see that you have custom field values. And I already created here different field values. So see that we have shear velocity. Okay, you have it here. So this is how you compute it, or how I compute it. So see that I created a sample. So see that here I'm accessing this line. So in this line, I'm sampling the velocity, the shear stress here. Okay, so see shear stress in this point divided rho in this point. In this case, is constant. You don't need to do it, but I just did it just to make it general. A square root of that. Then you have u plus, that is velocity magnitude divided shear velocity that we just computed. And then you have y plus, that you know your standard definition. Again, see that I'm accessing, for instance, mu in this line here in this point, but it is constant, so it makes no sense. So, or it makes sense if you are a compressor that you can get that value, but here is not necessary. And then here you have shear velocity, okay, that you just compute it, and this distance, this is the distance normal to the wall. Okay, so remember that you can compute that that is computed by default in Fluent, but you don't want to use this one, and you want to use your old values, your own values. Sorry. What you need to do is that, remember, the point here that you start to measure the distance, this needs to be the coordinate 0. So in this case, it's not 0. I recall that the 0 is here. So when you get that distance, it will be y minus this one. So you translate everything here and you start from 0 here. But well, I think it's a good standard practice to use the boundary normal distance. So see that you compute all those derived fields. Additionally, see that we have also integral length scales. So remember, from the theory, you can compute your integral length scales using the k epsilon model. This is how you do it. So you use the k omega, it's different. And also you have the ratio. Okay, here the ratio, okay, the grid refinement ratio. This is an indication to see where you can add more cells. So be careful that one is very conservative, and usually you will use that one in the core of the flow. But here, see that here we are in the gradient of the wall, so probably it's not a good indication because you have still the strong gradient, so it will tell you to have very fine meshes. So it requires some critical analysis when you're using that quantity. So, but let me go here, plot 3, and see that in plot 4, sorry, custom fields, the one that you created here, now you access that data, okay? And that data you sample here, and you have your plot there, okay? Remember that this is logarithmic scales, and you plot the other. So this is how we do it. And finally, just to finish the post-processing, let me go here and, okay, give me a minute that I have to answer the phone. Okay, so let's continue. So I was saying that this point, okay, you're plotting, let's plot the, okay, let me go here. Okay, so we have the velocity, okay, and let me get access to this quantity. So remember that these are custom field functions. So as you go here, you see L0, you have the integral length scales here. Okay, so this give you the idea of the largest vortices. Now this is computed from the turbulence model, and then we have RL, that is an indication, okay, that it will let you know if you need more cells just to capture better those integral length scale. And we talk about that the minimum should be something about 5, but remember that is for scale resolving simulations now. But here also this is a good indication now, because usually when you go to scale resolving simulations, you run what is known as a precursor simulation, get an initial solution, and usually it's a good idea to have those values, okay, when you are in here. So see that this is probably telling you that you need to kind of double your mesh, but remember, you need to look at the core, okay? This is indication at the core of the flow, okay? Close to the walls there, don't pay attention, because that you are there in the velocity gradient, okay, that is influenced for velocity gradient. So likely you will need to double your mesh to capture better there, but this is a rough indication, but it's better, like I say, better than nothing or just going trial and error. So pretty much we have addressed everything here. So let me go back here. We have all these plots, your quantities, and again here also in these custom fields, I think we have access to also again y plus. So see that we're computing y plus, and you have access to that value and all the fields. So you have access to u shear. Remember that u shear will be constant because we computed at one point. So everything that you add, you get access. And to get access to here in mesh, see that you have access to boundary normal distance. Okay, so see that you have access to all those variables and many other quality metrics. Okay, so it's very important also if you want to check stuff like phase area, things like that. You have access to all those quality metrics that later we will use these quality metrics to do some other operations. So this is this case. So as you see, we got a good agreement now, the starting point. But now let's rerun the case. But see that what we're going to do, that changing from the enhanced wall treatment, that is the recommended one, the one that will be kind of insensitive for the low Reynolds treatment for the KXL model. And I want to recall that low Reynolds means the Reynolds normal to the wall, not your system Reynolds number. So see here that you have different treatments, and invite you to read the documentation, press L, and you will see. But generally speaking, let's say, or some guidelines, is that non-equilibrium wall functions is like this one, but you have corrections for pressure gradient and so on. Scalable wall functions is the treatment where you find the intersection between the viscous and the log low, and then if you are below a value, you use this formulation. If you are above a value, you use the other formulation. And then the standard wall functions, this is the one that you need to be you need to have a y plus more than 30. So we know that here we have a y plus something about 10 or 8. So let's run this case and let's see what happens. Okay, so it's the one you can restart from the last solution, or you can initialize. I will restart from the last solution. Okay, so let's see what happens. So if I press calculate, see that usually always we have this jump and then all your quantities. Okay, so everything is being recomputed, but now we have the new approach. So now that we have a solution, okay, you can plot again here and see that you have similar result. But as you recall the previous one, this recirculation zone was smaller, the reattachment, it was shorter. So here we immediately see that there is a difference. Okay, but also in the mixing layer there you have a difference. So the best way to confirm that is just check the experimental results. Okay, so we have here the wall shear stresses, and go here and see that immediately you see that there is a difference. And if we plot the experimental, see what you have. So you can run, but see that in fact we have worse results. Okay, so this is very specific for this kind of model, the standard KXL and realizable and all these models. That is, you get finer meshes, you are going to get worse results. And as you go to the standard, will be the same. Okay, the standard is the original formulation. Remember, it's based in wall functions, but then it has been reformulated just also to solve the boundary layer. So I switch to this one, and I will expect also to have bad results. Okay, so now as I check here, see that again, these are even worse results. Okay, so this one you can see that different formulation will have improvements, okay, but not necessarily realizable would be the best one for all cases. So there are limitations, and again, this is the importance of reading the theory and knowing what each of these turbulence models is doing. So now let me go to the scalable. So remember that the scalable, what it's doing, and the best way to understand that, okay, will be if I go here and let me do this plot. Okay, so, and I will load here, load the wall, and load this and this. Okay, plot. So remember that you have this, okay, So this intersection here is something about 11 or 10.8, okay, 1125. So that depends on the concept. But the scalable, what it's doing is that is the value computed of y plus is less than this intersection, use wall resolving, and if it is more, use the log low, okay? And by the way, see here that in this case, look at how different is this, okay? Telling you that the results that are not reliable, okay? So this is the wall functions approach. So actually it's over predicting drag. So now that we chose here, let's move here, let's go to scalable, okay? So let's rerun and let's see what happens. So remember that now we're shifting that point and we're using another formulation depending on that value. We will expect to have better results probably. So let me go here. And if I go here that I have the validation data, see that we have in fact better results. They are not as good as the result with the scalable wall functions, but yes, they are much better results. And if I go here, okay, and let me plot now the other data. Okay, so in the files there, okay, I will put now this file and see that it's a little bit different, but it's much better than the previous one that it was all shifted below. Okay, so again, see that wall function, each of this treatment will have an influence in your solution. So as you go again here for the enhanced wall treatment, you have this non-equilibrium, okay, that probably you may have the impression that is the best one, okay, because you have the additional correction, but by no means that means that it will give you better results, okay? So let me put this one here and let's see what happens. Okay, sometimes they can be a little bit more unstable because they're adding these additional corrections that they might be detrimental for your solution. But it seems that in this case it did a good job. Okay, go here, put here, and actually it didn't do a good job. So see that how bad is the solution. Very, very, very different. Okay, so let's see if the problem is related to the formulation. So let me go to the RNG using that, and let's see if the RNG gets a better solution. So sometimes there are some of these wall treatments that might not be compatible with your formulation. So if we plot here, it seems okay, but this is the judge there. Again, we didn't get any big improvement. So now we go enhanced wall treatment is the one recommended, and if I click here, let's see what happens, and crossing fingers that this one will give the right results. Now that we already saw at the beginning that we have good results, but maybe as we have different solutions that will have an influence. So let's see. So see that now we have a much better solution. Okay, so I think at this point, play with this case. As you see, a lot to do. Stick with the K epsilon and play with all these models. Here you have different options, and remember always you have the help. So let me click here just to show. So that is the best source of information for you. Okay, so when you open the help, okay, in this case it went automatically there. Okay, the user guide, but also you go here and you have the theory guide, and in the theory here chapter 4, and here you have all the turbulence models. Okay, so as you go here, for instance, you have all the models, what is happening, and the wall treatments also. So you go here, should be the wall treatments you should have then somewhere here. Okay, 417, and see here that you have what is happening, and see that the non-equilibrium wall functions, okay, is let you know what is happening. But this case, it was clear that you saw that non-equilibrium that is adding all those corrections, it is worse in this case. So here in the data that you download, you have here the geometry. Okay, so if you want to do your own mesh, and here in meshes also you have a few other meshes. Okay, so you have a structure and structure just to show you. So as you read here, you can go read case. Okay, and I have here case mobs. Actually, these cases I already have the modification. So let me read the unstructured course. Okay. So again, just a reminder, also you will find a directory called settings. Here you have the settings. Okay. So you need to put these two files where you are reading the case or copying the case, because here you have the setting and here you have the velocity profile. Remember that we're reading those profiles. So just to show you this mesh. So what we have in this mesh, see that now, okay, we're doing now here, in this case, sampling here and sampling in the recirculation zone. So you know that here you're not going to get a good matching with the theoretical solution. But see that this mesh is very coarse mesh, okay? So here, let's try to run because this is already set up. So this is a standard, okay, k-epsilon with wall functions, okay? So yes, and let's see what we have. So see that our y plus is something about 80, okay? So usually if you want to use y plus, you should aim for values something between 60 and 100, okay? That will be the ideal one, but the upper limits depends on your global Reynolds number. So now we have a solution, everything fine. So let's see some colors. So see that immediately here you see the influence of the cell type in your solution, but we want to look at the solution in here. So let me plot in the bottom wall shear stresses, and now we can read validation data and see what we have, okay? So it is an acceptable agreement. There are some differences. Remember the wall function, the largest differences, you have it here where you have, you know, the back step, okay? But let's say that we have a good agreement. And now let me go and use enhanced wall treatment with this one, this mesh, and likely this should give worse results. Okay, so now we have this, and if I go here and open this, let's see what happened. Not big difference. There was here some change here that became worse, but still is given. Well, remember that the enhanced treatment actually, yeah, it shouldn't be a big difference. In this case it was worse, but remember that this one is the one that it will be y plus insensitive, you know. And the scale level also should give good results because it will find that point, the intersection point, and then it will choose a treatment. In our case, everything the y plus is always above that intersection point, so it will use log low. So it should give exactly the same results as the standard wall functions. Okay, so now I go here. Okay, and plot here. And we have this, okay. And what I want to show you here now, that see here that in the inlet condition we're using these profiles, okay. So this is very important because this will have a strong impact in your solution, okay. You have very realistic profiles. So see what happens. We use now uniform values. So this is valid also with the previous mesh, okay. So if you put that one, and here let me put this, okay. So what we're doing now is that at the inlet everything is uniform. Previously was this developed profile, okay. So what I did to get that one, you said what you do is that you get here the inlet and you get a longer section, and you let run the simulation in that straight section, and you get the profile at the outlet, and then you interpolate it here. Okay, so that is strongly recommended. Okay, having fully developed profile is more realistic. So let's run now using the uniform inlet. So we have our jump there and a fast convergence, and now let's see colors. Okay, so immediately we see some differences, but the truth will be here. So now if I open this, okay, see that we have very large difference in all this region. Probably here the match is relatively good, but see that all this region, the difference is large, and it's just due to the fact that we are using different boundary conditions, the uniform values. Okay, so in this case, we have seen the influence of turbulence models, different wall functions, different meshes, and also inlet conditions. Okay, so again, invite you to play with this case, a very nice case. We have this validation data. Okay, and that's all. Thank you for your attention. See you next video. Bye.